Um, Welcome, everyone. It's a pleasure for me to introduce our speaker for today. This is a Department of Mechanical Engineering seminar, but also an Australasian Fluid Mechanics series lecture. So welcome to those who are joining online, and thanks everyone for being here. It's my pleasure to introduce Hassan Nagib. Hassan is the John T. Retalatia, sorry if I mispronounce it, now professor at Illinois Institute of Technology. Hassan has spent his whole academic career at Illinois Tech, but has on many occasions held prestigious visiting appointments across the US and internationally. So anyone who's in fluid mechanics knows Hassan. He's been one of the great elders of the field and helped nurture many people here in Melbourne. So very appreciative to have him here for a month or so. As I said, he's recognized being a fellow of the American Physical Society, AIA, and many others, ASME and others. So it's a great pleasure to have him here, and we're very keen to hear his talk. As you can see the title there, on recent developments in mean flow, about mean flow Reynolds stress.
Thank you, Ivan. It's a real pleasure to be back here again. I've been here a number of times, and there are many memories that stay with me on every visit. And I'm trying to make some memories on this visit also and meet some new people. I need to recognize a number of people that help a great deal in this effort. And in particular, at the beginning, I'm going to talk about Peter Monkowitz. Peter and I have been partners on many crimes in publication. And he's just a superb theoretician with great appreciation for experiments also. In this work, we kind of drifted to a lot of numerical data, and as what DMS data in particular, as well as looking at many sensitivities of this data to various things, which I'm going to discuss. And the two key players are Ricardo Vinuesa, many of you know him, and Sergio Hoyas. And if you don't know Sergio Hoyas, he's a really impressive person. He's not easily recognized by his work as much as he really has contributed. Peter Schmidt from KAUST has been, and you'll see what the connection, and my own student, Victor Baxaras, who graduated already and is out in industry right now, working for an IT company that remains nameless. Okay. Is this the same issue? I'll do it this way. Okay, will it work now? Yes. This work sort of really focused a great deal after we had this workshop at KAUST about 9 months ago or so. Actually, it's 8 months. And it was focused on wall-bounded turbulence, and it followed in the spirit of earlier workshops we've had. There were 5 of them previously, and Ivan and I have been involved with them. I thought I'd show you a picture of the people. You can see Ivan. The 2 local hosts are up here in the front, and Rahul is somewhere in the back, I think, and Daniel. Also, Daniel, I think, is right there. Anyhow, we started with this workshop, and ultimately the information from the workshop is going to be available in various forms, including in a summary, which part of the reason I'm here is I'm working with Ivan on things related to that. The workshop basically had 5 themes, and I will kind of focus on 3 of them today. My involvement is pretty much on those 3. Others were involved more intensely on the ones not highlighted. So let me tell you what I'm going to talk about today. I'm going to talk about a new logarithmic plus linear overlap, which in our mind is a very interesting replacement for what we call the pure log. This is going to be about 10–15% of the talk, time-wise. The need for higher resolution, longer conversion, and possibly larger boxes for DNS. And as of this morning, Sergio Hoyas is sending me data about double precision versus single precision that really opened my eyes. But I couldn't integrate it into the talk. The majority of the talk really is between these two topics. And one thing you will notice is the focus of what we're going to do today requires the DNS because that's where we can do good spatial derivatives. Okay? Experiments suffer from a number of things. And then I'm going to show you some really hot off the press data from Cyclopia in Italy. Forgive me if I start on a very kind of fundamental and basic thing, but the workhorse of most wall-bounded flows has been the log law. For many years, we believed that for nearly 3 decades or more, almost 4, that the two coefficients, kappa and b, are constant, and we can use them in all possible configurations. In fact, most codes that you buy from industry to do turbulence modeling have these constants embedded in them. The one thing I wanted to show you early on is the differences between a boundary layer and duct flows. Boundary layers have a free stream and have a nearly laminar potential, at least, flow, while duct flows that I will show you a great deal don't have that. Now, this is the first interesting slide in the talk for those of you. About 2008, I can't remember the date exactly, it's in here, with Peter Mankiewicz and Kapil Chauhan, someone you know very well. We analyzed zero pressure gradient boundary layer with RE theta about 60,000. That gives you RE tau of about 20,000, 17 actually in this case. And what you see here, you see the inner part of the profile in both the mean plotted using a log and a derivative, which I'm going to use this word throughout the talk, which is called indicator functions. The indicator function is basically the derivative of this multiplied by the local distance from the wall. If it's constant, that means kappa is constant. And from here, we got very excited. We finally pinned down this, and I'll tell you how we got it pinned down, and this. But this is for zero pressure gradient, and it clearly does not equal those values that here. At the beginning, people were quite skeptical about some of this, but it has held quite repeated measurements, including here at Melbourne. What I'm going to tell you is today I'm going to demonstrate with channel and pipe DNS. I'm not going to do boundary layer DNS, and you're welcome to ask me questions because there are issues with boundary layer DNS, except for the adverse pressure gradient. That this was the exception, okay, to get a pure log. In fact, other than the zero pressure gradient boundary layer, we never find a pure log. And I'm going to show you that. We succeeded in doing this because we had developed a technique. Many of you know him. I know Ahmed's sitting in the back here. He uses it, oil film interferometry. And it gives us, I'm sorry that it's kind of covered here, accuracy that is equal to what you measure the viscosity of the oil. And it gets 1.5% consistently. We tried very hard for 1%. And it's not quite there. Okay, this allowed us to do things. Now I'm going to give you a bit of entertaining history. There is some German here, but I'm going to highlight it for you. In 1934, Karman wrote, he never called it the Karman constant. He wrote saying that Nikoratsid's data gave him a value of 0.38, nothing to do with 0.41. In fact, a few years later, and that's in German, he refers to his own paper, but gives the wrong number. Okay? And Rames Orlo, who reads German very well, kind of highlighted this in one of his papers. In fact, you don't find anything in Nikoratsid's data or Carmen's own and so forth that supports a 0.41. And why did we end up with the 0.41? It was pretty much because of some pipe flow that people like Don Qualls and my own mentor, Mark Markovin, and so forth, Peter Bradshaw, who I'm sorry to say recently passed away, had used. So in reality, the value was all over the place. And it was around the early 1950s that Ludwig and Tillman were the first one that called it the Kalman constant, and then it developed. Okay, that's a little bit of history. Well, Kapil Chauhan, and this paper has been around since around 2008 in physics of fluids, took the superpipe data, took many ZPG data from IIT and KTH in Stockholm and analyzed them. Channel flow is very tricky because the experiments are very hard to get to high Reynolds number and make sure they're two-dimensional and so forth. So there is somewhat of a limit on the range of Reynolds number. And what he did using, and I know some of you here know his composite profile very well for ZPG, but in the paper, if you read it, he has also composite profiles for pipes and channels. And out of that came out with this curve. Kappa seemed at high Reynolds numbers in pipes and ZPG to settle at a value. I think there is a lot of issues with the channel, so I'm not going to highlight. But the key point is, and this is Kapil's own creativity, when you plot kappa B versus B, if you differentiate dy dx, you get kappa. And if kappa is constant, this curve should have been a straight line. And I'm not aware of any collection of data that makes it a straight line without some width of tolerance, some accuracy limitations. Oops, sorry. So basically, there is the ZPG in here, and there is also data from others, including Flint Thomas from Notre Dame and a few others. Okay. Now comes the meat of the first part of the talk. So this was kind of historic. And since Kapil, by the way, this paper recently has picked up a lot of citations. So obviously people are beginning to hear this idea that the Kalman coefficient is really not constant. There are some really issues to try to match it to various models. And that's a debate that I'm not going to be able to get into today, but I would welcome any further discussion. When you do the Millikan matching, you match one term outer with one term inner, and you get the log law. Matching is not restrictive. You can do other variations. And in the matching, which later on will be referred to sometimes as MN, standing for Markovits and Nagib, and I apologize, that's actually Sergio's doing, not mine. If you match two terms inner and one term outer, you get an extra term, which is a linear term. It's much easier to write it in outer variables. So in addition to the log term, you get a linear term, which I'm going to show you in various ways in coming slides. How were we able to do that? There is a very unique, if you read Van Dyke's book, Neifer's book, you don't get the idea how to do this. There's only one paper by David Crichton, which was doing it in acoustics, because when the first term is log, it's very tricky to combine it with another term, but you can do it with what's called block matching. If you're interested, I'll give you the reference to Crichton's paper, which is very difficult to read, but it's very clear. So were we inventing something new? No. You go back to 1970, Yajnik talked about the linear term. His own student, Afzal, a few years later, talked about the linear term. Later on, in Lee and Moser, in fact, one time I was reminded by this, Bob Moser was sitting in the audience. He said, "You didn't read every sentence in our paper, Hassan, go back." And it's in there. And more recently, in Paolo Lucchini, who I know was visiting here recently. The big difference, the big difference, the linear term here is of the same order as the log term. They, in all of these papers, consider it as a higher order term. And in our analysis, because it's of the same order, it becomes dependent on the flow geometry, and I'm going to show you the summary, and the pressure gradient. Okay, so that's the big difference. Now you can see we're going always to theory, benchmarking with the experiment, but more recently, as I will show you today, we went to DNS because with experiments, it was a struggle. If you look at the indicator function for a log law and the indicator function for a power law, it was very difficult to differentiate. If it's gamma is constant, it's a power, but we finally, in the early 2000s, again, with experiments, were able to show that gamma is not really a constant. And since this paper appeared, actually, I don't see any papers in the literature espousing to the power law. And I'm going to give you a very interesting explanation to how the power law sort of emerged. We had to go to RE theta, if it's hard for you to see, about 40,000, which is about 10,000 plus RE tau. Okay. Yeah, I guess, I'm sorry. It's right here. We had to reach 10,000. When you take, this is DNS data. The reason I'm using DNS data here for a pipe flow is because it's nice and clear how to, if you plot the log, that's the dashed line. If you plot the log plus the linear that fits it, it has a much wider range. And actually the linear term picks up its its impact right here. Now, if I don't tell you that's a log plus linear for all of us that worked with power law, this actually looks like it's pretending to be a power law, okay? And that was the people, when they saw experimental data going up here and experimental data trending even more than the log down here, George and Castillo argued for that, and Barenblatt, but that has not sustained itself. Now, I need to give you a bit of an explanation on how do you get the terms, the coefficients of the log plus linear. The best data, and I really am impressed by that data, and I know a lot about it, and from DNS is the channel by Lee and Moser. 5,200 RE tau. And I remember when MK Lee first found this and called me by phone, and he said, "Oh, we found the 0.384. It's exciting." So we agree with the boundary layer. I said, "MK, slow down. Let's be careful." But I'll come back to that in a minute. But when you plot, if you take the indicator function, again, it's defined for you here to remind you, without the extra term, a plateau gives you kappa. If you do the log plus the linear terms, the log is basically the intercept. 1 over kappa gives you this intercept, and this slope gives you S0. Now, there is a parameter, just like with the log, and that is the upper limit and the lower limit. And we've been discussing this while I'm here, and we'll discuss it some more. I'm going to highlight it. The reason we stuck with pipes and channels and DNS is because, look up, sorry. This is for all the channel and pipe data I'm going to show you from now. These are not fits to the data. They're actual derivatives. We do derivatives up to 7th order, and we check things, and the data basically, the upper limit is not as clear as you would get. And you have to be careful not to go into the wake region. In the case of the channel, the wake is so weak that makes it very easy to do. The data of MKLE from this interpretation is exactly what Peter Mankiewicz and I last year or a year and a half ago had concluded the values. So these values are from this figure, and these values were in the paper. Now, let me explain to you. You remember the ZPG, that it kept growing and growing and growing. Maybe I should go back. I don't mind going back as long as yeah. Remember this? You go one Reynolds number, that's the red one, you go in the next one, and it keeps going longer and longer. Okay, this is the best DNS data for channel, and we focused on the channel in the literature. This is Hoyas at 550, Leon Moser, Hoyas at 10,000, Yamamoto at 8,000. Yamamoto, this is private communication. This is not in the literature yet, at 16,000, recently completed, actually in January of this year. That's a pretty high Reynolds number for DNS. He has the most powerful computer, practically, for DNS stuff. Now, if you look at this, and I'm going to tell you what these error bars are, you're looking for this extension and hoping for it. It's really not there, especially when you blow it up where the scale is representative of the tolerance. MKLE's data is that gray one. So if it was growing, the next one higher, the black one should have extended. The next one, the yellow, and they don't. Okay? Now, there is another very important criterion in match asymptotics, and it's not satisfied. And let me wave my hands. When you do match asymptotics, you have two limits. And when you scale it with the inner variable, all of them have to start at the same point. And when you scale it with the outer values, all of them have to end at the same point. And I must tell you, I've had a lot of debates with people, but it is, I mean, one place you find it very clearly is Knife's book. Anyhow, so it is not consistent with match asymptotic assumption for that reason, which was what you can see. The inner one keeps moving. When I plot it on inner variable, that's y plus if you don't see it. You plot it with outer variable, they don't quite end at the same point. Actually, the ending is not here. The ending is somewhere up here. So the log law is not clearly demonstrated in any of these DNS data, okay? And I know, I mean, I'm very familiar with Jason's PhD thesis and looked at it. We did not analyze too many experimental. In Kapil's original paper, we did use Jason's data, but not in the recent stuff. So let me give you a guided tour. This is the pressure gradient. A ZPG is beta 0, a channel is 1, a pipe is 2. This is kappa, this is S0. Kappa 0.384, gospel. There is no doubt. This is the dashed line, is the model by Mankiewicz and Nagib with what I explained to you before. But then we add both experimental and DNS data. Unfortunately, the DNS data in the pipe is not very good. There's still quite a bit, and I'm going to show you why. S0 grows, and S0 is much bigger in the pipe than it is in the channel, and that's going to be a very key. But let me give you a kind of advanced notice. We've spent billions of dollars, billions of computer time on the channel flow. We should have spent all that money on pipe flow for reasons. I mean, it's remarkable. But I mean, the channel has end effects, has homogeneous boundary in the pipe, make it Okay, and here it's hidden behind the thing, but that was the figure I reminded you of before, so I don't feel bad. Now comes to generalize and a bit more. Two experiments used oil film with adverse pressure gradient. One of them used oil film with adverse and favorable pressure gradient. This is beta, okay? Beta that we use here is based on an outer delta. And I'm going to show you that, why we do that on the next slide, okay? Not the classical beta. So these betas, you will find them higher than the betas you're all familiar with. There's a factor of 3 to 5 to 6, okay? This is the data from KTH. And behind the black little thing here, it says limited Reynolds number range. The KTH data is in a smaller tunnel. It's an hour goes all the way to 22,000 RE-tau. And when you extract kappa, S0, and B0 from this data, you get variation in kappa across the whole range. You get the ZPG condition right here. You get the channel condition right here. And you get the pipe condition right here. The blue ones are actually in these flows. And the other dots are from the boundary layer data. The blue are from IIT and the red from KTH. These are just guidelines, the fits to show the trend, which shows a strange trend here, kind of dipping. And from the DNS, those are the values that you get. Okay, I hope I haven't lost you. It's really a 3-parameter, and you have to extract all of them. Oh no, I better move this, because otherwise my joke is not going to be. So what's the solution? To look at this, I needed to travel to Korea, ICTAM, a month ago or so to listen to Ivan. And I needed to come here to work with his group. And I named the people that so far I've been working with. I hate this part of Zoom. The data that's added here from the Melbourne data is in green and was provided to me by Mitchell. And let me talk a bit about the beta. When you use the classical beta, you use delta star, which is the displacement thickness. There is no reason for turbulent boundary layers to use a delta related to displacement. This is a concept that comes from laminar boundary layers. So we needed to get a delta out of it. There are two different approaches. The one that's in this paper, oh no, I'm sorry. It's in the paper in the last slide. It's this paper here by Baxaras and Ricardo and myself. But locally here, and I let them talk about it, they have a different way of determining delta in adverse pressure gradient boundary layers, and the two, and in zero pressure gradient, and the two agree quite well. You probably will hear some local presentations on that. So this was the talk I listened to at ICTAM. All what I wanted to show here, that if you look at those last trends, if you revise them with the influence of these green points, and that's few of them with the local, you get a much more consistent trend that makes more sense to me, at least. And they all fall within that plus or minus 20%. Now, for some of you, you think plus or minus 20% is too big. I believe the fact they even fall on the same page is remarkable. I mean, there are so many uncertainties in the process of getting you there in turbulence, and we just need some guidance of where people in the future should focus. Okay, this is a revised version of what Kapil I showed you at the beginning, but I'll skip it for time reasons. Yeah, I'm doing okay. Now comes the part that has surprised a lot of people. I even made a comment that since I started talking about this, and Sergio Hoyas has been talking about, he just gave it a talk in Aachen, both of us needed to upgrade the amount of insurance we carry. Because we're basically saying the bulk of the DNS data missed the boat on how they should compute these cases. And let me show you some examples of why that is the case. Remember, I told you the pipe was very important, so we used the pipe. It's 10 diameters long. That's much longer than most of the data. It uses the code that's available to everybody to try. We started with very small Reynolds numbers, and we wanted to be challenged by the fact that for the pipe, you have to reduce your mesh, not only near the wall, but only on the center. Okay? In channel, you don't have that problem. Most approaches don't come down. You can see this is the typical channel values. The pipe case of Yao, which is with Schlatter and Hossein, we decided to cut that spacing by half. So when I show you for coming slide HR in red, that means it's twice the resolution of Yao. If their resolution was adequate, the two should agree. There will not be one single figure where the two agree. Okay? And we did this for various cases, so high resolution, low resolution. We also changed the azimuthal resolution, and the pipe is very tricky because as you change the azimuthal resolution, you go towards the center, you're also distorting the cells. Okay? Most people present results like this. Hidden behind all these green lines is a red line. There is no difference in the mean velocity, normal stresses of various kinds, or even the shear stresses between the high resolution and the low resolution. When you take the derivative of the mean velocity, okay, to get C, you don't see very much. If you look hard enough on this figure, you start seeing some deviation. So let us expand this. So what we do, it's expanded, and you can see the difference here. And what we do, we take 3 cuts in the indicator function and monitor them with time. This is eddy turnover times. Eddy turnover time is defined, maybe not in this figure, it's defined with U tau, and yes, it's defined with U tau and nu. Okay, eddy turnover times of 80 is unheard of. We used the Reynolds number of 550 because we could afford to run the computer this long. Most of the data in the literature, guess where it starts in eddy turnover times? Right here. None of these converge to the same values. Okay? They just keep going, each of them different. In the mean, derivatives. At this point, Sergio has said, wait a minute. I didn't write this code by Willis. It's very good code. It's great. It's easy to use. I want to trust my own code. So he went back to what most people call the Javier Jimenez code. It's actually Hoyas's, a lot of his own effort and others. And we went to channel flows. As much as I complained about channel flows, he wanted to use the code he was comfortable with. Again, we did the same thing. Look how many cases he ran. Different meshes, different length of the channel, different width of the channel. The classic case is what you see in pink with a little star on it. Here's what happens in the literature. Since the time of Kim Moyne and this group from Stanford, they did whatever study sensitivity. Everybody that publishes after that say, well, I use the same resolution, I use the same conversion they did, and I calculate at twice the Reynolds number. The next guy comes in and does the same thing with 3 times the Reynolds number until we got to 15 or 16,000. And nobody had gone back to see if the resolution, the conversions was adequate. We actually published a paper with Ricardo that claimed that when you get to a conversion of 10 to the minus 4, I'm going to define this. You can only do this in flows that you know what the answer to the mean shear. So in pipe, channels, you have a linear shear. Remember in undergrad fluid mechanics, we all know it. So you do the DNS, and you take at every step and compare the deviations from that linear one, and you do kind of an error analysis, and you integrate. And we thought, and across here with the various cases, you can see the pink one looks fine. And so we thought that that convergence was adequate. Tough luck. We went back with the new data from Sergio Hoyas. Channels are down here. Pipes are up here. The convention is still the same. Red is higher resolution than blue. None of them converge. I'm going to summarize here because this appeared recently in Physical Review Fluids, and the paper is right here. And we continued to do all of these different cases. And I just put this to show you what we were expecting from the best answer based on a lot of things I value here. And you can see it's all over the map. So how are you going to trust? And that's what gives you kappa from the flow, or gives you B or whatever. We were asked by the reviewers to prove something. They claimed that it was the way we can calculate, we were calculating. We've done the calculation, both fitting C or fitting the equation directly. You see the green dots here and the red line? They're identical. Okay? The mean flow has differences of the order of 2 to 3%. I'm going to show you that in a summary slide, which will surprise you, a couple of the comments there. But look at this. When I take a profile, and I know this is at a low Reynolds number, but I'm going to show it to you next on a higher Reynolds number. The only part that has small deviation between the log law and the data is up here. After that, it dips and goes down like that. When you take the log plus linear, it does not have as low as the log here, but look how low it is. We fit the log plus linear between 0.3 and 0.5 for pipes and channels. Boundary layer is a very tricky business, and that's something that Mitchell is looking at as we speak almost. Are you working on it right now, Mitchell? Good. Okay. At 10,000, it's the same story. The reviewers actually didn't argue with us about the raw Reynolds number, but we decided to answer them. The same thing. That's the only place. The log, small error. This is the place with the log plus linear. And it doesn't matter if you fit the C or you fit the equation, you get the same answer. Let me move this again and this again with the hope. So accepted idea that the mean converges faster than turbulence appears from these data not to be correct. In fact, the mean takes longer to convert. I showed you the RMS. So data shows that the first order statistics are below 1% when you get to 50, and it's not 10 eddy turnover times. The problem is to do these at high Reynolds number 50 or 25 eddy turnover times, most computer centers will not give you the time. I mean, you'll have to own the supercomputer. It really is that large an undertaking. So, but then you have to be careful. Are you going to extract something from the mean, and how meaningful to you? And I'm going to give you an estimate. However, the indicator function and the coefficient of the log and the linear terms, kappa and S0, or kappa by itself, extracted, remains sensitive to resolution even after 50 eddy turnover times. I need to move forward a bit now. Okay. I think this figure some of you will like. Maybe I hope more of you than not just some. For less uncertain, far less uncertainty in fitting the log plus linear than pure log. When you're looking at these plots, remember that this scale is 5 times bigger than this scale. So the bar, okay, it's probably hard for you to see it in the back, but I just gave you the approximate ratio. Now, oops. In the top, it's fitting the log. In the bottom, log plus linear. Left is the lowest Reynolds number. Middle is the middle Reynolds number. Right is the 16,000 case. Remember, there are 2 limits that we have to fit between. The lower limit is indicated on the x-axis. The upper limit difference from the lower limit is indicated up here. So the width of the period we're fitting is on the left. So for example, this star here, which is our preferred point, is that 0.3 to 0.5. 0.3 plus 0.2 is 0.5. Notice what happens. When you try to fit log, pure log, you can use all sorts of kappa. I don't show the B here. The lines are lines of constant kappa. The uncertainty is large. The trends are ambiguous, especially when you go here. I call it, it's like looking at the deep blue sea. You know, it's a very flat uncertainty. There is no peak to the optimization. While when you go with the log plus linear, you get a very clear pattern, especially as you increase the Reynolds number, and you can select. Of course, you have a choice of the value of kappa, but if you can see these figures close enough, they are not that different. Now I'd like to summarize this part, which was, I told you it's a major part of that. Millikan matching is not the only recipe, okay? And we're not claiming that ours is the, you know, the end and the best. Others can consider, but given the facts in the literature and so forth, we feel confident enough. With the exception of ZBG, the log plus linear is what we find. It's only the ZPG, which reveals that non-universality. This is really the part that I did from the DNS, and I actually just added this part an hour ago. Any quantity compared from the mean velocity will need very long averaging time, at least 25 ETTs. And even then, you still end up with 2 to 3% uncertainty. The values for kappa and B for the pipe and the channel, I'm going to show you something later. But this is, to me, one of the key results. And let me move this again. It is better to do Reynolds numbers in this range. Actually, 5,000 is a good 4,000 to 5,000. So in a way, Lee and Moser were kind of smart enough, lucky, I don't know, with high resolution, good conversions, a large enough box, than to just keep chasing higher and higher Reynolds numbers. Okay? Now I go to a topic that has had recently quite a bit of discussion in the literature. There are two, let me try to do this because otherwise my allergy will start me coughing. If you look at the literature, you find the wall-scaled eddy model. I know some of you might remember it as the Townsend attached eddy, but we prefer to refer to it in this way now, which gives you a logarithmic trend through the normal stresses, and more recently, based on bounded dissipation, Chen and Srinivasan, and actually Mankiewicz came up with this relation. This is data, DNS, again, for the same reason that I said at the beginning. At least today, we can do derivatives better from pipes and channel. Pipes are dashed, channels are solid. Now, look at this part. If you try to represent that data, even at the highest Reynolds numbers, around y plus of 1,000, which one do you pick, the red or the green? Unfortunately, this is not a scientifically sound way of doing it. And there is, I don't want to exaggerate, tens of papers in the literature that do it this way, okay? How are we going to do it? We take data from pipes and channel DNS all over the map. This has also appeared in the literature, physics of fluids. If you write to me, you'll see the hierarchy. And we do an indicator function. Again, the indicator function is the derivative of the normal stress, okay? If it is constant with a value, whatever, that means the logarithmic trend is correct. If you pre-multiply the indicator functions like this with 4y to the 3/4 and that derivative, if it's constant, then the bounded dissipation arguments, or at least, I'm going to refrain from saying bounded dissipation because at least the power relation trend is more correct. Okay. There are some important notes here, but let me skip them and I can come back to them because they just highlight some of the differences in the literature. But I want to show you something that justifies what I'm going to do next. And I think, Joe, you're going to like this. So, and you won't find it in the literature except for this paper here. If you take the gradient of the two stresses, the mean and the turbulence, and divide them, okay? And I think you've done this in some of your papers, okay? I think. You get these figures, and this is all for channel. If you plot it versus y plus, the inner flow near the wall is here. There is a switch over to the overlap region marked by this minimum here. You notice as increase, I hope you can see it with the colors, as you increase, the Reynolds number is moving to the right. Here, two things happen. As you increase Reynolds number, it's moving to the left, and it's suddenly becoming extremely close to the wall near zero. The difference, this is an inner variable plot. This is an outer variable. So you will see in the coming slides that when we use the indicator functions and outer variables, we get clearer conclusions from the results. On the left, plotted with inner variables, on the right with outer variables. I skipped the pipe. This is mostly channel just because it's easier to see. This is to confirm the exponential behavior. This is to confirm the power behavior. And here you can see a clear area and the behavior increasing with Reynolds numbers. You can see it starts spreading more and more, with higher Reynolds number. Now, you have to be careful. This is DNS. There are some limitations. Now, and I'll tell you at the end where some of this will be discussed. We are looking at the experimental data, examining the same things. Just to show you why I want to be guarded about using the bounded dissipation for the sole argument, it's a power. The bounded dissipation argues that the power should be quarter. We systematically changed from 0.2 to 0.25. That's a quarter, 0.28 and 0.32. And guess what? 0.28 appears to be better power. It's interesting that recently, Pirosli, based on some spectral arguments, reached the same number. I'm not so sure it's in the paper, but I know private communication between him and me revealed that. I'm almost ready to wrap. But before I do that, you remember my indicator functions for the mean flow? If I take all of the DNS data, you do the channel, it's down here. You do the pipe is here. This is the first time I'm putting the two together. We were mired, excuse my French, for so many years because S0 for the channel is small. Had we focused on the pipe, we would have detected. There is no log part in the pipe. Okay? In DNS. As far as the super pipe, previews of coming attraction sometime. The best way to determine kappa in the pipe is the way Zagarola and others have done it, and that's to follow the center line velocity. This data was obtained in Cyclope, mostly by the effort of Lorenzo, PhD student right there. I collaborate with his advisors on the work. Peter Schmidt happened to be visiting that day. The pipe is very, very long, 120 meters long, 90 centimeters, almost a meter in diameter, very well constructed. This is data over a year, over 4 years actually, but repeated over the last year several times. The green band is 0.2% uncertainty, not 2%, 0.2%. These are a number of different pressure transducers to eliminate the uncertainty in the measurements. Out of all of this, you get a kappa of 0.44. That is exactly the one that I just showed you from the DNS. It's right there, right there. Okay, the S0, which we extracted, but I didn't show it. It's interesting, two things. This is Pirosli's value compared to those. He has up to 12,000 now. And also the data of, it's shown a bit super pipe data of Beverly McKeon in here is also shown. I'm done. A few minutes, but let me summarize. The normal stress profiles do not exhibit either of the two, at least from the DNS, below 2,000. When you get to 1,000, you start seeing the power behavior, and it extends more and more, but there is a lot that needs to be examined. The experimental database from Melbourne, from Marusik's group, ZPG boundary layer, SAMI's data, most of you know, and the superpipe data are currently being analyzed. And we have a scheme, and I will present that at the APS meeting for those of you who will be there. Thank you.
Hassan, right from the floor of questions.
Many meetings.
Questions?
So,
I have lots of questions, but I only ask one, and then we can have more at dinner. Is the two-length scale approximation the inner outer overlap? Yes, outer length scale and an inner length scale.
that still holds.
No.
Yeah.
I understand. What I'm wondering is do you have any ideas about the inherent limitations of using two-length scales to represent a inherently multi-scale phenomenon?
That's a great question, and I know where it's coming from. And I can tell you that, I mean, you can ask the question with the attached eddy model, or how can you reconcile it with the log plus linear? It's basically saying that the change with the important scales is not straightforward linear. There are some nonlinearity in it. And in the normal stress, that appears to be the case. I think there is good suggestion that you need to include other than just the unique inner and outer, but we haven't. Peter thinks about this all the time. We haven't mastered how to bring it into the picture. But what I presented today, the log plus linear, does not violate that. One scale.
No, my question was more around.
No.
What's the
I had
bigger picture limitation?
Yes, I had. Yeah. I'm on a
Okay.
question.
Online. Kapil has a question.
Yeah, go ahead.
Hi, Hassan. Can you hear me?
Yes, I can.
Yeah. So thanks again. I will give you more details. The question I had is about the log linear and the region that you're fitting it. Okay. So conventionally, that is supposed to be the wake region. Anything beyond 0.2, 0.25 of boundary layer thickness or channel height. So my question is, how do we characterize something which is an overlap or inertial? Do we have any knowledge of what is the spectra doing? What is the range of scales, or what is so why do we call it an overlap region? And like, so that's my question in terms of, do we know more about the turbulence mechanisms in there?
Let me make absolutely clear that the outer region contains the wake and the overlap region should avoid the wake. That's what makes it very tricky in boundary layers and in particularly adverse boundary pressure gradient. In ZPG, it's not as hard, and in favorable, it is very clear how to separate. In pipes and channels, because as you know very well, Kapil, the pi value is the largest boundary layers, and it's less in pipe and it's less in channel. The wake part is extremely small and is limited, and using the boundary layer value of 0.15 or whatever you believe in pipes and channel is not a very good recipe.
Okay, thanks.
Yeah. Yes. Can you remind me of your name?
Marcus.
Yes.
It's good.
I've mentioned it before.
So, Hassan, thank you for the talk, and I really like the results from when you used to go the SQL plane and the SQL compatibility. Now, if you can ask experimentalists like me or Nick or Jason in terms of channel to do more, what do you want us to do? Like, should it have to be like a bigger channel or like a Reynolds number? Because to my best knowledge, some of the gold standard, of course, Jason's channel, but do we need to go higher or something like that?
Jason's channel is one of the gold standards, and he and I over the years have discussed the aspect ratio many, many times, but it's comparable to Zanoon's data, which I'm sure you're familiar with. The problem with the channel is the sidewall effects, the two ends, never stop interfering with you. And they are higher at low Reynolds number than at high Reynolds number, okay, the influence. You have corner vortices, and these also interfere. I think you don't need to go to high Reynolds numbers based on what we found from the DNS. 5,000 looked enough. However, you need to do something about the growth of the sidewall boundary layers. You grow the fully developed flow down the center line, but you need to, and I have to tell you, not in Zanoon's channel, but in the channel at IIT, we tried to put fences to eliminate this, and that caused more problems. Okay. Let's talk some more. I have been so focused on the pipe because it's much cleaner, and you do have a pipe here, right? Is it still around? Yes. Okay. Let's talk about it probably, but I am somewhat allergic to channels without some very careful consideration of all of these things. And chasing the highest Reynolds number does not give you the answer. But by the way, Jim, I am here. I sit in Daniel's office. My email is available to everybody. If you want to talk later, just come by or knock on the door or email. Jimmy.
I have a question on the north plus linear. So this overlap argument, without similar to Joe's, but so any overlap argument would suggest that your inner region should start at a fixed y plus. The outer region should end fixed y over delta.
Correct.
Now we know quite reasonably okay that the inner region moves out if you stick it y plus. So why would the overlap argument would work in the first place?
The last part of your sentence, Jimmy, is somewhat influenced by experimental realities. And the realities come from the fact that you have poorer resolution, or you have other effects, maybe even wall roughness effects and so forth. But I mean, by the way, there are, I think, a dozen ways, or at least 7 ways to develop the log law. The one that Tanakas and Lumley has in their book is one I don't like at all. And I say that whenever I teach turbulence course. You know, they say constant stress argument, and they get the log law. That doesn't work right. The only rigorous one is the matched asymptotics. That doesn't mean that the experiment or the physical realities have to exactly mimic what the match are. You have to find the features from the matched asymptotics and see if you discover them. But the part when you said that the inner moves out in DNA, it doesn't actually. Yeah, and what? I think those there may be the influence of other things.
Any other questions? If not, we thank you, sir.
Thank you. Can I log out of Zoom?